Okay, sir. So I can take over, right?
Yeah.
Okay. I see most of the people are from the last talk anyway, so I don't think I have to brush up any basics from the last talk. I think I can just jump into the topic right away. So welcome all. Today we'll be discussing Introduction to Differential Games. I think this is the third talk in the series related to optimal control and differential games, which is going parallel to the machine learning series or vertical. So here is the quick outline to the presentation for today. I'll start with some examples to kind of give you an introduction to game theory and what game theory is all about. And using those examples, I will try to motivate to understand what is Nash equilibrium and what is its significance in game theory. I'm sure most of you guys would have watched The Beautiful Mind, Russell Crowe. So it's the same Nash. So he's the one who gave us Nash equilibrium. Though, I mean, I should still bring up the names of von Neumann and Morgenstern, who theorized game theory or this essentially situations with multiple agents having strategic interactions. So I think Nash was kind of contributing to that theory or to that area through Nash equilibrium. And once we have Nash equilibrium, I'll just quickly introduce what is zero-sum games. It's just a small technicality, which we will use to understand, I think, the core topic, which is differential games for us. Once we have differential games introduced, similar to what we had seen in the last talk, which is the Hamilton-Jacobi-Bellman equation, here we have the Hamilton-Jacobi-Isaacs equation, which is exactly the same. You'll see there is no difference whatsoever, with a small technical added, that is all, but it's exactly the same. And once we have the Hamilton-Jacobi-Isaacs equation, we will look into perturbation games. I will introduce a single singly weighted game, very basic. I'm not going to solve any equations on the slides. It's a bit tricky. So I'll just introduce the solution to the game, and then I will move on to multi-purse or multi-weighted games, which is my research area. I'll give you some current results, and I think that will be the end of the talk. Okay, so what is game theory? In one line, it deals with mathematical models involving strategic interactions among rational agents, or those agents are also called players. Uh, Here, the important thing is about understanding what is rational. How do we define a rational agent? So on that end, a rational agent is one that always chooses the action with the optimal outcome, which means given a situation, a rational agent only thinks about maximizing the payoff, which we'll be defining in a while, in a couple of slides, but stick with me for a second. So given any situations, it wants the most out of it. It doesn't compromise, and it will always try to maximize by choosing the appropriate action. So with that assumption, because that assumption plays a very crucial role, and if I have time, I would probably discuss at the very end of this lecture what could it mean if you have non-rational agents, which I think is the most realistic aspect, because humans are not technically rational to the way it is defined. I mean, not that we're irrational, but in the game theoretic sense, we are not completely rational. So, okay, with that assumption, where we are looking into mathematical models involving these two or more agents trying to maximize their payoffs, here is one example that is, I think, very popular among game theory communities, which is what is called prisoner's dilemma. I think most of you guys already know this, but let me formally introduce this example. Consider the situation where the cops caught two robbers, or essentially two culprits, and they are put in two different rooms, and there is no information transfer between the rooms, and both are being interrogated. And in both agents' case, there are two options. The agent can either betray his friend and essentially give in to the cops' persuasion and say, okay, uh, give the testimony, or he can stay silent. And same is the case even for his friend too. So in that case, each agent or each player has two actions, which means there are four different scenarios, which can be written in this kind of table form, which means A stays silent, and I will call these players as player A and player B for the sake of simplicity. So player A stays silent, player B stays silent, and while player A stays silent, player B can betray and vice versa. And now in this four outcomes or these four possible outcomes, I will define the payoffs for the agents, which means let's say if both stay silent, both receive a payoff. So the payoff on the left is for A and payoff on the right is for B. So if A stays silent and B stays silent, each will get -1 payoff. But if A stays silent and B betrays, which means B is giving in to the cops while A is trying to be the honest culprit, in that case, A loses, which means he will have very less payoff or very high cost, which is -3, while B can just leave with zero cost or zero payoff. Similarly, if A betrays while B stays silent, then A kind of goes with a higher payoff while B loses with -3. And if both betrays, that is the interesting part, which is both will be paying cost, which is -10, which is less than, so which is actually technically higher payoff compared to when either of them betrays and one stays silent. So in this kind of scenario, the answer is what should they choose? What is the best way to go forward for both of these agents from the game theoretic perspective? Not that this is what's going to happen in reality, but game theory will give suggestions for those agents. What is the best way forward? So before we discuss what is the best way forward for these two agents, let me explain or let me introduce one other standard game, which is I think rock paper scissors, which most of you guys know would have played sometime in your life. So again, in rock paper scissors, there are two agents, and each agent has three choices: rock paper scissors, right? And which means there are 9 possible outcomes. And in this case, paper wins over rock, scissors wins over paper, and rock wins over scissors. And with that kind of idea, we can define payoff matrix in this form, which means if both chooses rock, they won't get in, none of the people get any payoff. It's a tie. If there is rock, if player 1 chooses rock and player 2 chooses scissor, then player 1 wins, which means he get payoff 1 while player 2 loses with -1. And similarly, if player 1 chooses rock and player 2 chooses paper, then player 2 wins with 1 and player 1 loses with -1. And you can populate it, all the 9 cells of this matrix in this way. And if you realize, if you add the payoffs of both players for a given outcome, you'll get 0. And which is why we call it a zero-sum game. So the technically the definition for a zero-sum game is you add the payoffs of the players, and if you get 0, that's a zero-sum game. So simple, right? The idea is one wins only if the other loses. That is the whole idea of zero-sum game, which means if one is trying to maximize his payoff, he's not indirectly or implicitly minimizing the payoff of the other player. So this is almost, this is not completely going against others' interests, as opposed to, let's say, in the previous game, it's not exactly going against others' interests, but in this case, you even winning implies the other one is losing. So this is another standard example in game theory, rock, paper, scissors. Now the idea is, how do we analyze the solution or the best way forward for the games, for the agents in this game? And the idea is Nash equilibrium. So again, I think most people get confused in the sense that Nash equilibrium is not what is chosen in reality or in the nature. There are relations, but Nash equilibrium says that the best strategy profile is the one for which no player can do better by unilaterally changing their strategy. What it means is, consider this situation where A stays silent and B also stays silent. Each one is getting -1, -1. So now for A, assuming that B is going to stay silent, he wants to check if he can do better than this, which means if B stays silent, if A betrays, he's getting 0, which means it is more than the payoff that he's getting in this situation, right? Which means he can quickly move on to this option under the assumption that B is staying silent. Similarly, look from the B's perspective. If B assumes A stays silent, then B clearly can do better by betraying, which means B also doesn't want to stay in this cell given that A stays silent, which means there is no quote unquote equilibrium, right? Which means under the assumption that A is going to stay silent or B is going to stay silent, the other one is going to deviate from the strategy. So what Nash equilibrium states is the strategy should be in such a way that no player can deviate from their current profile, which means consider this situation where A is betraying and B is betraying. In this situation, if again, you fix B's strategy, which is betraying, A cannot stay silent because, oh, 1 second. B betrays, you're fixing B, which means in this case, A can, oh, sorry, if A betrays, then the best he can do is, oh, sorry, my mistake. Sorry, if B betrays, I have to go unilaterally, right? My mistake. So if B betrays is fixed, then A cannot stay silent because under the situation he gets -3, but if he stays with betraying, he'll get -2, which is more than what he can get when he stays silent. Similarly, if assume that A betrays, B cannot do better by moving to silent because again he gets -3 instead of what he's getting in the betraying part, which is -2. So which means in this case, none of these agents can unilaterally deviate, which means if he assumes that other player is going to stick to what is the strategy profile, then he cannot do better than whatever he can do currently, which means this -2, -2, A betraying, B betraying is the Nash equilibrium for this prisoner's dilemma case. Okay, now we had seen the prisoner's dilemma. Let me formally introduce the notation for the Nash equilibrium or the game theoretic approaches. Till now we had seen 2-player cases, but it could be n players, n could be large, even infinity, where this sort of games or this sort of scenarios are pretty popular in what is called mean field games, but we are not going to deal with infinite number of players. We'll be dealing with, in most cases, 2-player games or more than 2-player or like n-player games with n being finite. So let me denote each player by P1, P2, P3, so on, Pn, and Pi means it's the ith player. And for each player, there are mi number of actions. And I call it the set AI, which contains this mi number of actions, and it is a finite set. Again, this is an assumption for simple matrix games for now. And which means if player I has mi actions, which means each player has M1, P1 has M1 actions, P2 has M2 actions, the number of possible outcomes is the product Mi. And now with this kind of scenario, I can define what is called the payoff function, which means given a possible outcome represented from the player I's perspective. What I mean is Ui is the action of player I, and U minus I is essentially the tuple containing actions of all other players except player I. So this is essentially the tuple containing the actions of all n players looked at player I's perspective. For this possible outcome, I define a payoff function pi for player I, which is a function of the actions picked by all n players. Which means for a tuple ui comma u minus I, each player or player 1 gets p1 ui comma u minus I. Player 2 gets p2, which is a function of ui, again u minus I. So on. Like there will be n payoff functions. Now, the Nash equilibrium is defined the situation where ui star comma u minus I star is a Nash equilibrium if for all I belongs to 1 to n, which means for all players, pi of ui comma u minus I star is less than or equal to pi of ui star comma u minus I star, which means this strategy profile ui star u minus I star is the best for player I, assuming that all the other players stick to their strategy profile and player I wants to deviate, but he cannot deviate because that is again the best payoff he can get for that for the strategy profile of all the other players already given to you. Any questions? I think this is the most important aspect of today's talk, which is Nash equilibrium. If you have any questions, I'll give a couple of minutes for you to respond. Okay, I'm assuming that everyone is everyone is with me. So let's move on. Okay, now we have the Nash equilibrium defined in this manner. Let's look at rock, paper, scissors. We had seen prisoner's dilemma anyway, and we know that in that case, both players betraying is the Nash equilibrium. But what about rock, paper, scissors? What is the best strategy according to Nash equilibrium? Let's consider 0, 0, which is player 1 choosing rock and player 2 also choosing rock. In this situation, if player 2 is choosing rock, player 1 can deviate to paper, obviously, because paper wins over rock. And also, which means he can deviate in this situation from rock to paper, which is for player 1. And similarly, what player 2 can do is, again, move on to paper. He can also move on to paper, right? It's not that he has to abide by this rock, comma rock strategy profile, which means 0, 0 is not a Nash. Oh, sorry. Player 1 choosing rock and player 2 choosing rock is not a Nash equilibrium. Okay, what about player 1 chooses scissors and player 2 chooses rock? In this situation, if player 2 is choosing rock, again, player 1 can switch to paper. And if player 1 is choosing scissors, player 2 can, sorry, my mistake. If player 1 is choosing scissors, then yeah, player 2, that's the best he can do. So player 1 can deviate, but player 2 need not deviate. But according to Nash equilibrium, no player should deviate, which means, again, scissors rock combination is not a Nash equilibrium. What about player 1 chooses paper and player 2 chooses rock? In this situation, if player 1 is choosing paper, player 2 is choosing rock, player 1 can switch to, one second, I don't know if I made a typo here. If player 2 is choosing rock, then player 1 can, player 1 can only choose paper because that is the best he can do. But if player 2 is if player 1 is choosing paper, then player 2 can choose scissors, right? Because scissors win over paper, which again, player 2 will deviate in this situation, but player 1 need not deviate, which means paper, comma, rock is not a Nash equilibrium. So similarly, if you keep going through all the 9 cells, the rest of the 6 cells, you will realize that none of these combinations is in equilibrium, because in each case, either of the players or both players will tend to deviate from their strategy profile by the nature of the game, which means you can say there is no Nash equilibrium, or more precisely, till now what we had discussed is what is called pure strategy Nash equilibrium, which means at a given instant, a player will choose a fixed strategy. There is no sort of probability distribution over actions, which is what is defined as mixed strategy Nash equilibrium, which means consider the situation that the game is being played multiple times. And instead of choosing a fixed strategy, he can choose the action based on a probability distribution over the action space, which means I can choose rock with probability P1. I can choose scissors with probability P2, and the probability for choosing paper would be 1 minus P1 minus P2, because if you add all three probabilities, it should be equal to 1. So if I have this sort of probability distribution for actions for both players, now the idea becomes what is the best probability distribution that I have to choose that can maximize my payoff, which is what is captured by the mixed strategy Nash equilibrium. And in this situation, even though a pure strategy Nash equilibrium doesn't exist for rock, paper, scissors, it can be shown that a mixed strategy Nash equilibrium exists, and that is essentially choosing each action, every action with equal probability, 1 over 3, 1 over 3, 1 over 3, which means you go completely random. And that is the best you can do according to game theoretic Nash equilibrium approach. And an important result that is part of Nash equilibrium is every finite game which involves finite number of players and finite number of actions will have a mixed strategy Nash equilibrium for sure. So this is essentially what is called the existence of Nash equilibrium theorem, which is proven by Nash, which got him the Nobel Prize. And even though a game need not have a pure strategy Nash equilibrium, there will always exist a mixed strategy Nash equilibrium. So one criticism or one concern is mixed strategy Nash equilibrium can be used if you're playing the game multiple times. Only then you will be able to see your expected payoff being coming up as you play over infinite number of games. But what if I'm playing just one game? Then yeah, I mean, you can probably go with a pure strategy Nash equilibrium if it exists, but even then you can go for a mixed strategy Nash equilibrium and flip a coin and be like, okay, whatever comes, I'll choose that. So that is what typically game theorists suggest as per the result that Nash had given us. Okay, so that's with rock, paper, scissors, and what is called mixed strategy Nash equilibrium. Do you have any questions on this front? I don't know if I had gone a bit faster on mixed strategy Nash equilibrium, so I just want to be sure if you're on the same page.
Ramnath, this saddle point also you can say.
Oh yeah, so actually, an equilibrium is also called saddle point. I think I missed that simple information. So every time people call equilibrium, they mean saddle point, or if they say saddle point, it is equilibrium. It's the same. It is equivalent. Why it is called saddle point is again because you have this sort of definition. Let's just go back. So it is a saddle point because it is the best in every direction. If everyone is trying to maximize their payoffs, saddle point is where, that is the local maxima for every player in every direction. So which is why it is called a saddle point. And in this case, we also call it Nash equilibrium, but they are one and the same. Okay. So till now, we had discussed what are called simple matrix games, which means it involves two players and you just draw a matrix because they only have finite number of actions, and each action pair has a payoff which can be put in the cell of that table. What is the differential game? So if you remember the standard optimal control setup, I think you're quickly able to realize that instead of a cost, we have a payoff function, which is now a function of two control inputs. And in this case, the standard differential game involves two players. You can generalize it to n players, but for the sake of simplicity and just to keep things bit tractable, let's stick to two-player differential game. So player one is choosing U and he wants to minimize the payoff, while player two is choosing V and it wants to maximize the payoff. So which is why I call player one the minimizing player, and I'll be calling the player two the maximizing player. And what the payoff function has is a terminal cost, which is again a function of, I'm sorry. Okay, sorry, I think that's a disturbance, my mistake. So the payoff function has terminal cost, which is a function of the state at final time and the final time itself, plus an integral cost, which is the running cost, function of the current state, the control picked by the minimizing player, the control picked by the maximizing player, and the time. So this is exactly the same setup, but then instead of one control that you are trying to minimize or maximize an optimal control setup, you have two controls, while one control is trying to minimize and the other control is trying to maximize this function. Of course, the state, I mean, since it's a differential game, there should be a differential equation involved. In the typical matrix game, you don't have any time component. It's just, it's what is called a static game. You'll be playing it once or you'll be playing it multiple times, but there is no idea of time or dynamics involved. In this case, it's a dynamic game with differential equation, which means the game is evolving in time and the evolution is governed by differential equation, which is why we call it a differential game. And the dynamics is again standard x dot is equal to f of x, comma u, comma v, comma t. Instead of just one control, again, in the optimal control setting, we have two controls driving the state, u of t and v of t, and we were given some initial condition for the state x at t naught equal to x naught. We'll say the terminal condition for this game where you say that, okay, the game has ended given by this equality or this equation, which is psi of x at tf, comma tf is equal to 0. So in terms of notation, we assume the state is from n-dimensional real space. The minimizing player is choosing controls from an m-dimensional state space, so m-dimensional space, and the maximizing player is choosing its action from an L-dimensional space. So there is no restriction that the action spaces of both the players should be the same. It could be different. There is no restriction on that front. So what does it look like? I mean, I think I have differential game says, okay, one is trying to minimize and one is trying to maximize. If you remember what I just said a couple of minutes, what I said a couple of minutes back, it is a zero-sum game. So this way of writing a differential game will lead to a zero-sum game because one player trying to optimize, I would say, instead of minimizing or maximizing, I would say optimize, will go against the interests of its opponent or the other player. So in this case, you can call this a zero-sum game. And given this situation, the equilibrium is defined using what is called upper games and lower games. Okay, so consider this scenario. You are given the game, or both players were given the game, saying that this is the payoff function, this is the dynamics that you should be following, and this is the terminal condition. The upper game is a situation where the maximizing player is already given what the minimizing player is going to choose. Notice that in the differential game, as similar to what we see in optimal control setting, we are trying to search a function, not a single action at a time, right? It's an infinite dimensional object that you're trying to figure out that optimizes the cost. So which means the maximizing player knows the function, be it in feedback form or open loop form. And I'm assuming that all you guys have attended the previous talk where I had given examples and a description about what feedback means and what open loop means. So in both cases, regardless, let's say the function is given, be it open loop or feedback for the maximizing player. Now we can choose based on that information. And in this case, it becomes an optimal control problem. You fix the control of one player, which means it is just a one-sided optimization. We can solve it with standard optimal control techniques. And if the maximizing player will get its best input as a function of the input of the minimizing player. And in this case, the value as defined in the optimal control case, the value of this upper gain is defined as min of u max over v of u j of u comma v, which means given u, the maximizing player is optimizing over that information. and what is the best u that the minimizing player can choose again. And that is called the upper value. And similarly, in the lower game, it is vice versa. The minimizing player knows the input of the maximizing player, and then it picks its input as a function of the maximizing player's input, and you can define what is called the upper value, the lower value for this lower game. And the Isaac's min-max condition is this: the upper value and the lower value should be equal for the existence of a saddle point or an equilibrium. And the corresponding u star comma v star for which this happens is the saddle point itself. And in this case, you can see these u star comma v star, the solution or the saddle point, as a fixed point, which means you have gotten this, the strategies or the function, optimal functions for the upper game and lower game as a function of the other player, right? You have v as a function of u, which is v bar of u, and u as a function of v, which is u bar of v. In this situation, what it means is v star is essentially v bar of u star, and u star is u bar of v star. So if you can solve these equations, then you would get the saddle point equilibrium that satisfies this Isaac's min-max condition. And in this case, again, going by the game theoretic definition, you would have j of u star comma v is less than or equal to j of u star comma v star less than or equal to j of u comma v star, which means given given u star, v star is the best because v is trying to maximize. If it chooses anything other than v star, it is going to get a lesser payoff. And similarly, given v star, if since u star is trying to minimize, if it chooses anything other than u star, it is going to get increase its cost. So this is how you characterize a solution in a differential game scenario. So this is how you define equilibrium or saddle point for a differential game. Now, how do you find this u star comma v star? And the answer is the Hamilton-Jacobi-Isaacs equation. Again, here I cannot stress, but you would quickly realize that the Hamilton-Jacobi-Isaacs equation is exactly the same as Hamilton-Jacobi-Bellman equation. So much so that, I mean, if you are, just to give some little historical perspective on what has happened or what people say had happened, is this. Both dynamic programming and differential games were developed in what is called Rand Corporation in US. It used to have the highest number of scientists who got Nobel Prizes and who used to work for defense-related purposes. And it was Isaacs who was working on this differential game theory and was developing this Hamilton-Jacobi-Isaacs equation in 1950s. So he did most of the work, and he was giving presentations in the Rand Corporation. And people say that actually Bellman saw one of his presentations, got inspired, and came up with the Bellman equation even before Isaacs was able to publish his results in 1965 or 64. So Bellman was actually credited for the famous Hamilton-Jacobi-Bellman equation, but people say that Isaac should have gotten the credit. So that's the little history lesson for you. But coming back, again, if you want to obtain the solution for a differential game, you would first define what is called the value function. Again, the value function is the optimal payoff from starting from time t, which means from that time onwards, both players are choosing their optimal control inputs u star comma v star, which would give rise to the optimal trajectory, which is x star, and the corresponding payoff will be what is called the optimal value. Again, this optimal value function is driven by the Hamilton-Jacobi-Isaacs equation, which is a partial differential equation, which is minus of partial of v with regards to t is equal to, this is the running cost, L of x star comma u star comma v star comma t, plus partial of v with regards to x times the dynamics, which is f of x star comma u star comma v star comma t. Again, as we had seen in the optimal control case, the terminal condition for this value function is the terminal cost function. So you have this. Again, you can define what is the Hamiltonian in this situation, which is L plus lambda times lambda transpose times F, which is the dynamics. And you can obtain the adjoint equation for this lambda, which is lambda dot transpose is equal to minus of partial of h with regards to x. And the transversality conditions will follow again. Lambda transpose at TF is equal to the partial of your terminal cost function with regards to state plus a multiplier times the partial of your terminal conditions with regards to x at the final time. And the Hamiltonian at final time is again the partials with respect to the final time. And the optimal control inputs are given by, I don't know, I don't remember people calling it a Pontryagin's min-max principle or something, but you can probably call it that way because you have a min-max situation as opposed to a minimum situation or a maximum situation. So U star comma V star is essentially that controls that minimizes H for a given U while maximizes H given V. So this is how you can obtain optimal control inputs for both players using the Hamilton-Jacobi-Isaacs framework. But in most cases, as you had seen in the optimal control setup, it's not easy to solve this partial differential equation. And if you go for general multi-agent setting in a differential game situation, there is no hope for solving this differential equation. In most cases, of course. So let's start with most popular differential game scenario, which is what is called pursuit evasion game. I'll start with the two agent game situation. We call the two agents, one is pursuer and other one is evader. And you assume that both players have dynamics that talk about simple motion in a plane with velocity constraints, which can be defined as the position of each player is driven by this differential equation. X is the position, U is the speed, and the speed is bounded by U max. So in this situation, we assume that the pursuer is faster compared to the evader, and the objective of the pursuer is to capture the evader in minimum time, while the evader wants to maximize the capture time, or you can say postpone the capture time indefinitely, if possible, to infinity. So the idea is here, the payoff function is TF, and you have the dynamics given by these equations, and you have the initial conditions, say the pursuer denoted by the red color is here, and by at some xp0, and the evader initial position is, let's say, at xe0. What should the pursuer and evader do? The answer is the pursuer should follow what is called a pure pursuit strategy, and the evader should follow what is pure evasion strategy. What it means is these are, again, what are called optimal state feedback strategies. At every instant, given the position of the evader, the pursuer has to draw a line joining the evader with its current position and keep its velocity vector along the line of sight. And similarly, the evader's strategy is to go opposite to that line of sight direction. And in this situation, the idea is capture exists if the pursuer is faster compared to the evader. If not, the evader can evade indefinitely and there exists no capture. So this is how you characterize the solution for a single pursuer, single evader game where players have simple motion with velocity constraints. And in the case of pursuer being faster compared to the evader, you have capture, and if in the case evader is faster compared to the pursuer, or even if the evader is of the same speed as the pursuer, you don't have any capture, which means in this situation where both players have same speed, both players' relative distance doesn't reduce, which means there is no capture at any point of time. So this is essentially a single pursuer, single evader game, which is very simple. But in the current scenario where there are a lot of UAVs that are coming up into the skies, one of the important aspects that I'm interested in is to address what is called air security. You can have a lot of rogue UAVs, rogue drones, and there could be airspaces that need to be secure. For example, let's say when you had seen this in the news to, for example, you have UAVs coming around, let's say White House or any of these Parliament building or Rashtrapati building. You have those are secured airspaces, and you don't want any of these small drones or UAVs flying around those important buildings. So how do you uh, manage airspace security? How do you, the first thing you should do is capture that UAV. And actually, I think it is in Denmark, people have tried capturing UAVs by training hawks or eagles, and they didn't have good success, and the whole program bombed. I mean, the uh, eagles or hawks became rogue, or sometimes they didn't do the intended task, and it was a big failure. So if you cannot capture a UAV with a bird, what would you do? You capture a UAV with another UAV. That's the best way. Fight a robot with another robot. And I think it was the company Drone Hunter that's kind of very popular now, which is creating drones that can capture these other drones and is talking about airspace security. And it is getting a lot of traction. This is an interesting problem where, let's say, given multiple drones in an airspace, how do you go about capturing all the drones with, let's say, another group of drones that you can deploy? So you can call this a multi-purpose or multi-evader scenario. So given a territory, there are, let's say, E1, E2, so on. EM are the rogue drones that you come across. You have, let's say, N agents that are guarding the territory, P1, P2, P3, so on, Pn. How should these N agents go about capturing these M evaders? And you can assume that the speeds of these agents are different. This is the most general case. And you assume, again, constant speed with heading control, which is simple motion. And one of the important assumption that is required to even talk about capturing all these adversaries or intruders is this. Essentially, the slowest pursuer should be faster compared to the fastest evader. If not, you cannot capture any of the evaders. Oh, sorry, you cannot capture all the evaders. You can probably capture those evaders that are slower compared to some of the pursuers. But if you want to capture all the evaders, then all the evaders should be slower compared to all the pursuers that are there. And how do you go about solving the problem? If you write this associated Hamilton-Jacobi-Bellman equation for this scenario, there is no hope for you to obtain a solution. One approach is essentially looking at the idea of divide and conquer. Instead of solving a big n-pursuer m-evader game, solve m multi-pursuer single evader games. In this situation, you can actually allocate pursuers to evaders by some metric and try to solve these individual games. And in this scenario also, since it is more than two agents, which means, let's say, even there are two pursuers, one evader, it's not so easy to solve the associated Hamilton-Jacobi-Bellman equation, or the Isaacs equation. Sorry, it's one and the same, but yeah, I want to keep myself technically correct, so I will call it the Hamilton-Jacobi-Isaacs equation. Since again, in this situation where you have multi-pursuer single evader situations, that you cannot solve the game, and one way to address this issue is dumb down the problem a little bit, fix the strategy of the pursuers. And I think Professor Kothari will discuss this in the next lecture, discussing missile guidance, where you would see what is called the constant bearing strategy. And I'll discuss what is the constant bearing strategy in a while. So if I assume that the pursuers are following a constant bearing strategy, now I can figure out how I can allocate these pursuers to all these evaders. And that way I'm able to solve this quote unquote unsolvable multi-processing multi-evader problem with these simple assumptions and tricks. Let's see what is a constant bearing strategy. In a constant bearing strategy, given the evader's position and heading, the pursuer will calculate what is called the collision triangle, which means if the evader keeps traveling in this heading for all time, assuming the pursuer is faster compared to the evader, it can figure out what could be the collision point, and it can redirect itself to the collision point at every instant of time. And this is called the constant bearing strategy. It needs, again, uh, the current position and velocity. And in this situation, the bearing angle, which means the line of sight, the angle of the line of sight with respect to an axis will remain constant for all time. And the instantaneous distance will reduce at every instant of time, under the assumption that the pursuer is faster compared to the evader. So if I assume this, I can define what are called active or redundant pursuers, which means I'm not fixing the evader strategy, but I'm only fixing the pursuer strategy. So the evader at this point, if it knows that the pursuers are following constant bearing or whatever strategy that you fix, let's say even if you fix pure pursuit strategy, it can figure out its best strategy given in that situation and solve an optimal control problem. So I define active and redundant pursuers as the situation, I mean, like in a situation where for a given evading strategy, if there exists sorry, my mistake. Let me retract that. A pursuer is, oh, sorry. Oh, sorry, my mistake. Pursuer is active if there exists at least one evading strategy for which it can capture the evader before all the pursuers can capture the evader, which means in this situation, I can define what is called the time to capture, which is the minimum time so that there is at least one pursuer in the capture zone of the evader. And the capturing pursuer set is the set of pursuers that are in the capture zone of the evader at the time of capture. Okay, which means if I have to define an active pursuer, there should exist an evading strategy where that pursuer is in the capturing pursuer set. And if there exists no evading strategy for which the pursuer can be in the corresponding capturing pursuer set, then it is a redundant pursuer. The idea is if it is redundant, then there is no point for the pursuer to even follow the evader or go behind the evader. It can very well save its resources, which is very important in the case of a quad rotor or a UAV with fixed battery power. So now the question becomes, how do you identify this active or redundant pursuers? And the solution is with what is called Apollonius circle. So again, Apollonius circle is defined as the locus of capture points for a non-maneuvering evader, which means if the evader's initial position is here and the pursuer's initial position is here, given the evader's heading in one direction, if it keeps going in that direction, whatever is the intersection of that line with the Apollonius circle will give the capture point for that evader and given the pursuer's initial position. And the good thing is you can actually come up with closed form expressions for this Apollonius circle for a given pursuer and evader pair. So once you have the Apollonius circle for a single pursuer evader pair, you can define what is called the Apollonius boundary for multi-pursuer single evader scenarios. So the Apollonius boundary is a subset of points belonging to the Apollonius circles, and each point in the as part of the boundary is the closest to the evader along the line of sight originating from the evader. So once you come up with this sort of Apollonius boundary, the conjecture I came up with is this. I don't have a formal proof with at this point. It's a bit difficult to come up with the proof for even this sort of multi-agent scenarios, but I was able to come up with simulations, and as far as simulations are concerned, it works. The pursuer is active if its Apollonius circle is part of the instantaneous Apollonius boundary and redundant otherwise, which means given the initial positions, I can obtain the Apollonius circles in closed form, and that will give me the Apollonius boundary too. And if I know that the pursuer is not part of the Apollonius boundary, I can call it redundant and let it rest. In this situation, if you see, the Apollonius boundary only has the pursuer's P1's Apollonius circle and P2's Apollonius circle, which means only P1 and P2 are active, and P3, since it is not part of the Apollonius boundaries, the Apollonius circle is not part of the Apollonius boundary, which means P3 is redundant. So with this sort of idea, I can now solve the situation where given an intruder in a secured airspace, I can assign pursuers based on the instantaneous Apollonius circles and let it let the agents pursue as long as they're active, and the redundant pursuers can stop and rest. So this is a quick simulation where I have 5 pursuers and 1 evader. And you realize in the initial time, this cyan pursuer is anyway redundant, and each pursuer will go redundant as time progresses until the green pursuer captures the evader. So this is one way of solving multi-pursuer, multi-evader scenarios. Multi-pursuer, single-evader scenarios. But I can use this idea to extend it to multi-pursuer, multi-evader situations. So in the case of multi-pursuer, multi-evader settings, one pursuer can be active for multiple evaders. And one way of breaking the tie is choosing the evader that can be captured in shortest time possible, which means I would look at this quantity, which is the distance between the pursuer and the evader pair divided by speed, the sum of the speeds of the pursuer and evader, and whatever is the minimum uh, value, and the corresponding pair will be chosen for the assignment for each pursuer. I think I'm losing on time, so let me just skip these slides and show one simulation where I'm able to solve the multi-evader scenario. So here is 4 pursuers and 2 evaders, and using a time-breaking condition and assigning pursuers that are active to the corresponding evaders, and redundant pursuers being stopped or put at rest. This is one way to arrive at a possible solution for multi-pursuer, multi-evader situations. This is one simulation, and here is another simulation. Here in this case, I have 10 pursuers and 5 evaders. Okay, so this is part of my research, and I'm trying to work on including turn radius constraints. For example, in a situation where the dynamics are not simple, and you want to include constraints like turn radius, rates, and all that stuff, things become more and more complicated, and I think those are more realistic. So currently my work is about how to include turn radius constraints in these scenarios and arrive at solutions. So with that, I end my presentation, and I'm open for questions, please.